All right, hello, welcome back. So let me begin by reminding you what we are doing. We have started working with a new concept, work and energy. These are extremely useful because they are scalars. They don't depend on time. So if I want to write work that we defined, you remember it was f dot dr from some point 1 to some point 2. So this ended up being a scalar, and we could do a lot of good things with it. We could relate this to the change in kinetic energy. We saw under some conditions the total energy, mechanical plus potential, would be conserved. That would also give us some leverage in some of the problems. So all of these, great. One thing to note here is that there is no time in these equations. And that was the good thing, the good part of this set of equation, the framework we were working with. That we didn't have to worry about how much time has passed. Everything was location dependent. But let me make the case that time is still very important in many of our problems and applications. To see why, consider you're creating a crane. It's a 100 kilogram and you want to lift it up maybe 1 meter. And you're tasked with designing this crane. You want to know what kind of motor you need to do that. To properly size the motor, you would need to think about time. So try to imagine two scenarios. One is you want to lift this in 1 second. And in another scenario, maybe 1 minute. The amount of work you need to do is still going to be the same. You have to lift 100 kilograms times gravity times 1 meter, and that is 981 joules. Doesn't matter what you do, how long it takes. This is the amount of work you need to provide to lift this box. But if you want to move it in 1 second, you need a beefy motor, a huge motor. Whereas if you want to take your time, spend 1 minute, maybe you can even get away with having a motor. You can have a crank, and with a rope, just with human scale power, you can just crank it up and eventually you lift 100 kilograms. So time is still an important concept that we need to take into consideration in many of our problems, because it is important how fast you do that work. And that brings us to the concept of power. Power in definition is work per unit of time. So how much work has been done in how much time has passed. So if you were to calculate the power under these two scenarios, P1 in this case would be 191 divided by 1 second. And in the other case, it would be 981 divided by 60 seconds. And you will see that you have a much smaller power here. So that concept, P average, we can divide it as total amount of work from one point to another divided by total time that has passed. And this is the power of that force doing the work. And like before, when we were talking about kinematic variables, this is over a finite time period. I don't know, 1 second, 10 seconds, 1 minute. If you want to know exactly how much power is going through your system at any instant, you can take this delta t, make it smaller and smaller, and you reach the instantaneous power, which is limit when delta t goes to 0 of u over delta t. Let's call it delta u. And this, is du over dt. So power is rate of work or time derivative of work. And now you see, you can connect the dots that you have. Usually these motors or any of the actuators that you can think of are rated for a certain power, like a small motor is usually in the order of a few watts. Oh, by the way, the unit of power, let me mention that. Unit of power is joule per second, or we call it watts after James Watt. I think it is spelled W-A-T-T-S, watts. That is the standard unit. You may encounter other units. Horsepower is a famous one. And in the imperial system, often pound inch, pound foot. These are the imperial. No way, that is work. Pound inch per second. Yeah, actually I don't know what is the unit in imperial system. Yeah, maybe pound inch per second. Who knows? Certainly I don't. Watt is a lot more common when watt and horsepower are more common units of power when you're actually working with sizing the motors and actuators. So what did I want to say? I was saying, when you want to size your motor, for instance, for your crane example, you can see here you need roughly 1000 watts. Here you need 1000 divided by 60, that's 100 divided by 6, 50 divided by 3. Now I'm stuck. How much is that? 15, 16? 16. 16 watts. Huh? I think. I don't know. Something like that. My mental math was never good. And you can go and search for motors that can provide you with this amount of power. I think that's good enough for now. I can leave the definition for here, a few remarks for the next video. So I'll see you in the next video.